Okay, so when I was invited to this talk, I didn't know how much I should speak because I titled the talk OpenFOAM Accelerating Research in Academia and Industry. But before that, I'll just give you a brief history of my association with OpenFOAM. And it goes back, and I just recounted it, goes back 2 decades, more than 2 decades now. So I feel really old. I just want to quickly show you one snapshot from the second OpenFOAM workshop in Zagreb, Croatia, 2006 Jan. That's, if you were to clock back, it's almost 20 years. Since then, I'm somewhere in the crowd. I see my PhD advisor over here. And that's the journey with OpenFOAM. We started back in the day, a ragtag set of people. No, you don't need to applaud anything. It just makes me feel old because there are people in this room who are probably born after that date, right? So there are people in the room who have been born after that date. So my association with OpenFOAM goes back a really long way. So I am pleasantly happy to see how it has grown, how it has been adopted, not only in the West but also here, and increasingly both in academia and industry. So my association with OpenFOAM started with working on a PhD problem, and at that time we were, back in 2004, 2005, if you had to solve a CFD problem, you had to write your own code from scratch, okay, from scratch. So that's a big challenge. You had some utilities, you had some libraries, you could, call some math libraries to solve some linear algebra problem and all those things you could do. But more or less, if you had to solve some sort of problem which didn't exist in commercial solvers, you had to write things from scratch. And that was very daunting. Daunting, especially because, you never knew whether you'll be able to complete your PhD in time, right? And obviously, can you then start looking at grander challenge problems, bigger problems, etc. So one of the first things, so by the way, I'm not going to bore you with any equations or any bits of code in this talk. I took some inspiration from the preface of Stephen Hawking's book, Brief History of Time, where he says that for every equation you put in a book, you lose half the viewers, right, or half the readers. So I have consciously stayed away from putting equations here in this talk. But this was the first problem that I started working with when I began my journey with OpenFOAM. And the task was, we were trying to model what is called as non-equilibrium phase change in fuel injectors. And this was a real problem in the sense this is 2005, 2006. The world was interested in, obviously at that point of time, and it still is interested in increasing the efficiency of gasoline engines. And one of the technologies that they were experimenting with, and the bigger automotive manufacturers they were experimenting with, was something called as GDIs, or gasoline direct injection. So if you're aware of how an internal combustion engine works, especially standard petrol engine, you realize that you inject the fuel close to what is called a stop dead center, or when the pressure is at the highest point, and then combustion takes over and energy is produced, so on and so forth. Standard IC engine cycle. But one of the problems with port fuel injection is that the fuel does not mix properly inside the combustion chamber. There is an issue of wall wetting with the inside the piston cylinder arrangement, and there is wasted fuel, unburned fuel, which sort of escapes in the cycle, right? And so that obviously drops down your fuel efficiency. So one of the thought the engineers had was, okay, instead of injecting the fuel at top dead center, let's now inject it at close to bottom dead center, or when the full suction stroke is done. Okay. Now, the problem with that is that you have pressures in the combustion chamber below ambient pressure because the suction stroke is done. So as you're putting in the fuel, because the pressure is so low, will start vaporizing, right? It will start vaporizing, and there's a danger of vapor lock, right? So that's one thing we need to understand. The second thing is, how do we model this? How do we model this fuel injection process? Because the pressures are going so low, you're going to start seeing vaporization within the fuel injector itself. So typically in normal fuel injectors, you have full liquid fuel going and the vaporization takes place only inside the combustion chamber. But now, because the pressure, back pressure is so low, you'll start probably seeing vaporization within the fuel injector nozzle itself. So how do you design this nozzle? How do I understand the physics of it? And to add to the challenge, this is not a single species liquid. Petrol contains several components. It has octane, it has lighter fractions, heavier fractions. It's generally a mix of many things. So it's essentially a multi-component hydrocarbon. Okay, so multi-component hydrocarbon, but as a single species. Then the second problem is, how long does this injection take place? So typical car runs at about, if you're idling the engine, it's about 800 RPM. If you're driving it regularly with normal load on the engine, not climbing up a hill, etc., it's about 1500 RPM, 1200 to 1500 RPM, depending on how your, engine is configured. Your injection time is a small fraction of that cycle, right? So 1500 RPM typically means 4-stroke cycle. So divide by 2, and then you can figure out how much time it takes for one particular full cycle. Injection is a small fraction of that. So it's really small amount of time. It's a few milliseconds, barely few milliseconds, or it's almost few tens of microseconds where the injection actually takes place. Now in that time, the fuel, when it is vaporizing, what we think as engineers is that the moment a thermodynamic state is reached, right, pressure, temperature, all the other properties will reach there immediately. But that is equilibrium thermodynamics. But in that short period of time, there's no equilibrium, right? So there is some finite lag for which this needs to come in. So now you have to model the phase change with thermodynamic non-equilibrium. Now think about the complexity of the physics in it, right? Now I have to model multiple species or model some surrogate fuel. I have to model the non-equilibrium, and then I have to take care of real world injector geometries. I cannot just do this in a straight tube and say, hey, problem is done. This is a real world. This, by the way, is an actual fuel injector from Bosch, which goes into an operational GM engine, right? So think about the complexity of the problem, and you don't have 15 years to develop this. I mean, if I had taken 15 years to do it, writing code from scratch to model this, by then EVs would have come and this is gone in history, right? I mean, you have to do this cycle. What really helped us is OpenFOAM. Okay, OpenFOAM was in its early days. In fact, it was FOAM till 2004, and then they open sourced it in 2004. There was a small community, primarily out of Imperial College, Henry Weller, Herv Yasak, and others. Then Herv got a faculty position at Zagreb. He moved there. He worked with few people. We were one of the few people in, I was a student in the United States at that time. We were one of the few people who started working there with them. And we decided, let's try this modular approach and to see if we can develop something quickly enough and test it for real world engineering problems. And I was fortunate, things worked. With research, nothing is guaranteed, but things worked. We were able to, develop this quickly enough. And within a period of about 3.5 to 4 years, we were actually able to give a validated code for engineering sort of calculations to General Motors. So much so that in their production cars from 2008 onwards, they actually used this model inside to model the fuel injectors, design GDI type of engines. Similarly, the same model was used to model non-equilibrium flows for jet fuel, Jet A and JP8, and this was used for Pratt & Whitney's engines by United Tech, right? So the modularity of this code helped us to sort of really accelerate a lot of the complex industrial type calculations that we need to do, okay? And that's the story I'm going to tell you today. So what sort of different problems that we have attacked in the last couple of decades. I can't talk about all of it because some of it is under IP and I can't talk about it in open. Some of it is ongoing. Some of it there were failures too. I'm not saying that everything is hunky dory, right? You can't have everything succeed all the time. So this was one of the first problems that we worked on. Then as I got to IIT Bombay, we started looking at fundamentals of jets and cross flows. And this was sort of important for us, looking at the fundamental dynamics of how jets break up in cross flow. This is a complete multi-phase flow problem with Rands type closures for turbulence. And we wanted to study the characteristics of the breakup of this jet. And the reason was that, again, it was an industry-driven problem of trying to look at land-based gas turbines, fuel injection in land-based gas turbines. So you're injecting liquid fuel into the combustors of gas turbines. There was a cross flow, it would break up. We wanted to see how these breakup modes would occur, again, to look at fundamental, breakup characteristic, breakup, then mixing efficiency, so on and so forth. This is again a similar problem to the jet and cross flow problem. Here, we used a volume of fluid sort of approach where we were not explicitly tracking each and every phase, right? So because we were using a volume of fluid approach, we had to resolve a lot of features, right? And that means it was computationally very, very expensive for us. So we could only do basic fundamental studies with it and then come up with sort of better correlations in terms of atomization models and breakup models. The next problem where this helped us was over here. So this is basically an Lagrangian Eulerian type of problem where you again have, in this case, injection of water into a cross flow of superheated steam. And the water sort of breaks up into many, many small droplets and then finally eventually will vaporize. Now you will ask, what is the purpose of this? So this is used as a control mechanism in thermal power plants, right? So the idea of thermal power plants is that you generate a lot of heat. The heat is used to produce large amounts of steam. The steam goes and drives a turbine, produces power. But when the superheated steam is produced, one needs to modulate and control the temperature of the superheated steam because the combustion process will generate steam at extremely high temperatures. But when the steam actually goes through the system and hits the turbine, you need to have some sort of control at what temperature the steam is hitting the turbine. Because if it hits at extremely high temperatures, you will have material destruction of the turbine blades, which are very, very expensive. So the way, how do you control high temperature steam? How do I modulate the temperature? The way is that I inject water, right? So you inject water, basic thermodynamics kicks in, first law kicks in. The water vaporizes, takes away energy from the steam, and then you have this delicate balance. But here's the challenge again. I need to understand how the breakup of this water takes place, the atomization of this water takes place, how it vaporizes, how much the temperature drop is there, okay? And is there any residual water left? Because imagine I inject, if I under-inject water, I am not going to cool the steam to the desired temperature. If I over-inject water, I not only waste energy by overcooling the steam, but there is a strong possibility that not all of the water will vaporize, and then you have a bullet. You literally have a bullet because water is 1,000 times more dense than steam almost, and it's going to go and hit the turbine blade with that much momentum, right? So you're going to cause further damage. So you have to understand this entire process and you have to model this. And this is not easy. I cannot resolve. Remember, the size of this pipe is about a meter, right? You go to a large 500, 600 megawatt steam power plant, this pipe is about a meter in diameter. Your droplets are micron size. I cannot fundamentally resolve each and every droplet. It's computationally, you give me, forget the supercomputer sitting here, you give me the world's fastest supercomputer, yet it's not a tractable problem, and it's not worthwhile throwing that much energy into a problem because the energy that is being produced by the steam power plant is probably not enough to pay for that computation at that point of time, right? So how do you solve it? You solve it using arbitrary Lagrangian Eulerian. So you model these droplets as Lagrangian particles, Lagrangian parcels in the cross flow. You put in correlations. I will again not go to the math. If you want to talk about the math, you can come. There's an entire paper, there's an entire report about it. But again, we were able to do these calculations within a year. We were able to suggest to the company which is producing the steam power control valves, hey, this is the prediction from CFD. We validated it against experiments. We did some fine tuning. And then we say, okay, here are the atomizer design changes you can make to make this mixing more efficient. We did a similar problem for something called as pulse detonation engines for a ballistic slab. This is another interesting problem which we used volume of fluids for. This is steel converter simulations. So a steel converter, this is for a Japanese steel company. The steel converter is basically where you have molten steel and you're hitting this molten steel with extremely high velocity compressible air jets. The reason is that you want to agitate this molten steel so that all the slag and the impurities in the steel sort of comes up in the surface and you take it off. Challenge here, molten steel, 7,000 to 1 density ratio, compressible air, 1 kg per meter cube, steel 7,000 kg per meter, 7,000 to 1. It's 7,000 kg per meter cube steel is sloshing around, model it accurately, and then to see how these injectors can be placed optimally so that you have, reasonable sloshing, reasonable mixing, so that the reasonable slag, extraction can take place. Magnetohydrodynamics. So this is the test blanket module for the ITER fusion reactor, and you can see the scale of the human being here. So there's a breeder section here. So one of the things the fusion reactor needs as a fuel is deuterium and tritium. Deuterium is not plentifully available. Deuterium and tritium needs to be created through a process, and it's created in a process called TBM or in a test blanket module. So what is a test blanket module? It basically has flowing lead lithium alloy. Okay, lead, one of the heaviest metals known to mankind, lithium very, very light, mixed together, eutectic alloy is flowing through. It's a magnetohydrodynamic fluid. And in that, helium, so you basically are having a nuclear reaction which is producing deuterium, and byproduct of that is helium. And there's a possibility of a helium ingress in that, right? So this is being done in a very, very strong magnetic field. So we have to model this as a magnetohydrodynamic fluid, right? So we were trying to understand the physics of the magnetohydrodynamic flow at extremely high Hartmann numbers in this TBM module. Also again in OpenFOAM. Biological flows. So we talked about a lot of industry. Biological flows. So when the pandemic hit, there was a lot of CFD being used to study different types of flow dynamics. One of the theories, the doctor came to me and said, can we study the flow characteristics inside the nasal passage, right? Because one of the mechanisms of the vector was that these pathogens would go through your nasal passage, and some of them would get sort of stuck in the nasal passage, and some would go inside. There are ways to sort of rinse it out, but to understand that process, we had to understand the flow dynamics within this nasal passage. So we actually took, if you look very closely, that's my nose. That's actually my nose. So I took my MRI, reconstructed the mesh, and put it up there and tried to study the flow dynamics inside it. So this is a project which didn't take off too much because the science of, the rinsing off, the pathogens, etc. was not really sound. But the idea was that we wanted to study the fluid mechanics, right? While it didn't go anywhere, it was a hobby project, but it was fun to do it. The fact was that we were able to take such a complicated geometry, right? I mean, think about the complicated geometry of the nose, especially my nose, very complicated. And we were able to model it all the way up to the back of the esophagus right here. So this is the green part is the entire cavity. And we were able to sort of model that. This was another interesting project we did with doctors at the KEM hospital in Mumbai. This was trying to look at, blood flow, especially in portal vein system, and mostly for patients with liver cirrhosis. Now, the issue with liver cirrhosis is that the portal vein system sort of terminates towards the liver, okay? And there are a bunch of capillaries which then go in into the next part of the digestive system. Those get completely clogged in patients with cirrhosis. So there are lots and lots of clots, etc. So sort of pressure builds up over here. And once the pressure builds up, what happens is that some capillaries will burst somewhere, usually in the digestive tract, and usually the patient sort of bleeds out through the digestive system. That's typically what happens to these patients. So the surgeon had an idea that, hey, if I can put a shunt to relieve the pressure, right? If you relieve the pressure, then you might not end up with those capillaries bursting, etc., and bleeding out. But where do you put the shunt? How do you put the shunt? So for that, you need to understand the flow mechanism in this portal vein system. This is actually, again, this is not my portal vein. I have a perfectly healthy liver, thanks to everything. But this is from a patient who was unwell, and we were able to sort of, look at this, the flow dynamics within the portal vein system, and also make sort of analysis of where the pressure builds up, and that sort of can guide the surgeon to, where can he or she put a shunt in the system to relieve the pressure. So what I want to drive from this talk is that you can see the diverse ways where we can apply this technology, right? CFD can be applied in many places, but the fact that somebody like me whose forte is just modeling, right? I'm not a doctor. I don't know anything about portal vein system. I am not a metallurgist. I don't know anything about, molten steel. Okay, I'm a mechanical engineer. I do know something about power plants. I'm not a nuclear scientist. I don't know anything about TPM. But the fact that my strength is, I always say, give me a PDE, I will solve it for you numerically, not analytically, numerically. And I can do it very quickly using a toolkit like OpenFOAM. That's the beauty of it. And I can solve extremely complex problems using things at extremely large scales. Now, I'll show you a couple of more problems which we have not solved using OpenFOAM, but hopefully someday I will want to solve it using OpenFOAM. This was done using some other standalone codes. This is a problem of the 2004 Indian Ocean tsunami, right? So looking at the tsunami origin, how the waves spread, I'll show you an animation of this in a bit. And then once the tsunami takes place, this is the coastal inundation. So the wave actually comes and there are some buildings, etc. How does it flood the coast? So these are sort of the same problems, but sort of delinked in certain ways. We are using different techniques to solve this. We are using different numerical methods to solve this. My hope is that someday these techniques, so the other advantage about OpenFOAM is that, as Professor Bose said and Ms. Payal said, it's open source. We can keep modifying this code. We can keep adding stuff ourselves. So we would like to add these numerical techniques into a toolkit like this so that you can actually sort of utilize it. Okay. So I'll just quickly show you some animations before I close the talk. This is the 2004 Indian Ocean tsunami. You can see the wave arriving. You can actually see the wave go all the way to Africa. People measured the tsunami all the way in Africa. While the majority of the damage was in Sri Lanka, eastern coast of India, Thailand and Indonesia, the measurements happened all the way here. In fact, they even measured the tsunami wave in Goa, which is on the western coast of India. I'd like to also show you, this is the injection of water in this, the steam control valve. By the way, all this is validated stuff, okay? So it's not just carefully fudged data or CFD. This was another interesting project of an agitator in a food processing plant. So there was this agro industry which came, said that they had this different ingredients which would go into this large agitator and they had to mix it. And they wanted to optimize the agitator arms, where to sort of place it, right? So that you could mix it most efficiently with least amount of energy. So this was a problem. And this exploited everything, AMR, moving reference frame, so on and so forth, right? And lastly, I would like to show you, this was the steel simulation. You can see the sloshing of the steel, which is happening over here, the liquid steel. That's the steel air interface. Yeah, so what are we doing now further with OpenFOAM? The current projects that we're working on modeling ALD, atomic layer deposition. This is mainly for sort of semiconductor manufacturing of semiconductor chips. The other thing that we are looking at is modeling electrolysis for alkaline electrolyzers. This is with the hydrogen economy, right? So there's energy which is being generated either through green sources like wind and solar, even gray through thermal and hydro plants. But if you want to transform it to the hydrogen economy, you have to generate hydrogen, and it's done through the process of electrolysis. So where we are looking at trying to optimize the shape of electrodes using CFD simulation. Okay, with that, thank you. I'm open for a few questions if there's time. Yeah.
Tell us some of the solver names that you have.
Okay, very good. So for the VOF solvers, it's basically interFOAM. Okay, the non-equilibrium phase change is a custom solver which we developed on our own. It's not part of the standard release. We have not shared it publicly, but on request we can share it. There's no problem with that because it was sort of IP back in 2009, 2010, but now we are open to sharing it. We have used that solver now to model other things also, including modeling non-equilibrium phase change of ammonia mixtures, modeling refrigerants. So, but we are happy to share that.
And may I ask also what kind of meshing tools that you have used?
Okay, good. So meshing tools is a big challenge in OpenFOAM, as you realize. Generating good meshes is the art to see. So if you have fairly clean geometries and regular geometries, even complicated shapes but fairly clean watertight STL meshes, we typically rely on block mesh and SnappyX. But if it is little worse than that, and where we need some geometry cleanup as well, Gmesh is my go-to.
Basically, the most complicated there was I think the Vine.
Yes. That was block mesh and SnappyX mesh. Okay. Block mesh and SnappyX mesh. Yeah. So actually, that looks complicated, but it's not that complicated. It's not that complicated, to be honest. Including the nose, it looks complicated, but it's not that complicated to generate that mesh. Thank you.
Thank you so much, Professor Shiva. I will just request Ms. Usha to please come. She is our senior project manager. Just Usha, if you can just give him the token of appreciation.